Okay, now we're going to derive a very important kind of form or formula. This is for the Taylor series generated by f at x equals 0. And that's really what we had, was a Taylor series with a center at 0. And when the center is at x equals 0, that's actually called a Maclaurin series. In general, if the center is A, it's the Taylor series. And when A is 0, we call that particular Taylor series a Maclaurin series. So, and we're going to come up with a formula, and you're going to be able to use these to construct these series in a little bit more defined manner. So let's say this is our polynomial function as we talked about before in exploration 1, a sub 0, a sub 1x, a sub 2x squared, a sub 3x to the third, a sub 4x to the fourth, a sub 5 x to the fifth, a sub 6x to the sixth, and for as long as we want to go. All right? So f of 0, when x is 0, you notice that these terms all go away, and f of 0 equals 0. F prime, we take the derivatives, and you see how we took the derivatives. That's going to be 0, that's going to be a sub 1, that's going to be 2a sub 2, that's going to be 3a sub 3, that's going to be 4a sub 4, 5a sub 5, 6a sub 6, and then these exponents are going to be diminishing by 1. So f prime of 0 equals a1, as we did in exploration 1. Then we take the second derivative, and this is going to 0, the derivative of that constant is 0, and then we've got 2a sub 2, and then 3a sub 3x squared. And if we put 0 in, all these terms are going to go away, so we've got f double prime of 0 equals 2a sub 2. Now, notice that if we solve for a sub 2 now, this is going to show us, this is going to imply that a sub 2 equals f double prime of 0 over 2. Now we can go back, and we had a sub 1 equals f prime of 0 over 1. Okay? And we could say that a sub 0 equals f of 0 over 1 also. Okay? Now we can take the next derivative. So if we take the derivative, this is going to be 2 times 3, 3 times 4, 4 times 5, 5 times 6, all right? Although at 0, these are all going to disappear, so we're going to have 2a sub 2. Again, as we just said, I'm sorry, well, we already did that one, but I didn't show you the other terms. So you get a sub 2 is the second derivative divided by 2. Now, if we take the third derivative, then we're going to have, this is going to go to 0, and then we're going to have 2 times 3a sub 3, and then we're going to multiply that, so we're going to have 2, 3, 4, a sub 4, 3, 4, 5, a sub 5, all times x squared, and then 4, 5, 6, a sub 6, x to the third, etc. And then at 0, these are going to vanish, so we're going to have f triple prime at 0, or the third derivative, is equal to 2 times 3, a sub 3. And you can see how we have a sub 3 equals, if we divide both sides by 6, a sub 3 equals f triple prime over 2 times 3. All right? Which is 6, which is 3 factorial. All right? And then we can go ahead 2, 3, 4, a sub 4. Then we take another derivative, so we're going to have 2, 3, 4, a sub 4. And this will go to 0. Then we're going to have 2 times 3 times 4 times 5, a sub 5, x. And then 3 times 4 times 5 times 6. And you see we're getting these factorial situations. But at 0, these are going to vanish. So we're going to have 2 times 3 times 4, which is 4 factorial. So f to the fourth derivative equals 2 times 3 times 4, a sub 4. And that implies that a sub 4 will equal the fourth derivative divided by 4 factorial. And we can keep doing this. And we'll end up, if you see the pattern, watch the pattern. Keep taking these derivatives. All right? and you just keep multiplying by another 1, so you're getting these factorial progressions. So we take the fifth derivative, this is going to go to 0, this is going to be 2 times 3 times 4 times 5, and this is going to be another 2, so 2 times 3 times 4 times 5 times 6, a sub 6x, etc. So the fifth derivative will be 2 times 3 times 4 times 5, which is 5 factorial, a sub 5. So a sub 5 equals the fifth derivative at 0 divided by 5 factorial. So notice how we have these factorials. So if we put these are my coefficients, so we put the coefficients in. For my f of x, my function, we have f of x equals f of 0 over 0 factorial. That was all the way back over here, because we can think of this a sub 0 as f of 0 over 1. Well, we can think of 1 as 0 factorial, so it matches. So you can call that 0 factorial. So a sub 0 equals f of 0 over 0 factorial. A sub 1 equals f first derivative, 1 derivative over 1 factorial. A sub 2 equals second derivative over 2 factorial. A sub 3 equals third derivative over 3 factorial. A sub 4 equals the fourth derivative over 4 factorial. A sub 5 equals the fifth derivative over 5 factorial. So it's real easy to remember. So we put these coefficients. This is like x to the, you can think of this as x to the 0 power, which is 1. So we have all these zeros. F of 0 equal f of 0 times x to the 0 over 0 factorial. And then if we put our a sub 1, which was f first derivative over 1 factorial, that's my a sub 1, so times f x to the 1, you see how we have all these 1s. First derivative, 1 factorial, and first power. Oops, sorry about that. And then if we look at the a sub 2, a sub 2 over here was f double prime. Second derivative, 2 factorial, a sub 2, that's going to be times x squared. So we have second derivative, second power, 2 factorial. The next one would be third derivative, third power, 3 factorial. Fourth derivative, fourth power, 4 factorial, etc. All right, so you see the pattern. It's a very easy formula to remember how to derive these polynomial approximations for these functions by using the derivatives of the functions. So I'm going to put it all together over here. But I think you can kind of recall from exploration 1 that we had p sub 0, 1 equals 1, p prime is 2, 3, 4, 5. And the power series we came up with was this one. That's from exploration 1. Which actually is the same thing as p sub 0 over 0 factorial, p sub 1, p prime of 0, or 1 factorial times x to the first. You can see second derivative, second power, 2 factorial, third derivative, third power, 3 factorial, fourth derivative, fourth power, 4 factorial. So you see the factorials work. And also recall from example number 1, the natural log we came up with was the same idea. Same series which matches the same pattern. P of 0 over 0 factorial, and this we can think of this as x to the 0. X to the first derivative, first power, 1 factorial, second derivative, second power, 2 factorial, third derivative, third power, 3 factorial. That's what we came up with in that example 1, where we're trying to approximate the natural log of 1 plus x. So this all leads to the definition of the Taylor series. So this is the Taylor series generated by f at x equals 0. Now when it's at x equals 0, it's the Maclaurin series. We'll talk about when it's at x equals 2 or 3 or whatever a little bit later. So again, here's our definition. Let f be a function with derivatives of all orders throughout some open interval containing 0. Then the Taylor series generated by f at x equals 0 is f of 0. Now, actually, if you really want to do it right, f of 0 times x to the 0 over 0 factorial, and this would be f prime of 0 and 1 factorial. And you can see 0, 0, 0, 1, 1, 1, x to the first, 2, 2, 2, etc. And then we end up with f, the nth derivative, f evaluated at 0, x to the n over n factorial. And then we could write this as a summation when k goes from 0 to infinity, and this is your Taylor series. Centered at 0, which is called the Maclaurin series generated by f. And there's your general formula, summation. The kth derivative evaluated at 0, x to the kth over k factorial. So that's our Maclaurin series. And I think for your first 4 homework problems, you just had to generate it said, construct the 4th order Taylor polynomial at x equals 0. That's just the Taylor series, or actually just the Maclaurin series. That's what that is. It says the Taylor polynomial at x equals 0. So there's your formula. So that's kind of how you derive. That's how you derive. That's how it makes sense. Okay, so I hope that helps, and you should be able to handle the first 4 homework problems now. And you could take a look at, example 2, constructing a power series. Now, they did it without the actual formula, just more intuitive, but you could use the formula. Maybe we'll do that in class. Okay, so main idea right over there. And that formula is in your textbook on page 487. And there are some graphs, and you can see how the approximations get closer and closer to the sine graph, and then we'll probably go over that in class tomorrow. Okay? So that should give you some insight as far as what to do on the first 4 problems.